of God, Ram Ram. I am Kumar K, and today I will help you with the GoldMan Sachs online assessment. Many students are giving GoldMan Sachs online assessment. The CTC is 30 lakh. Okay, many third year students, fourth year students, and working professionals are regularly giving the online assessment of Goldman Sachs, and they ask really hard DSA questions in the Goldman Sachs online assessment. Okay, so please know that if you want to crack Goldman Sachs online assessment or any other company, top tech company online assessment, you need to have two skills. The Because we are programmers, let's start with index number 0. You should have very good English comprehension skills, okay? English comprehension skills you need, because they will always give you large English paragraphs, and then you will have to analyze the question and summarize it in 1 to 2 lines for yourself. So for example, if I scroll below, this was the question asked recently in Goldman Sachs online assessment, a break and add problem. Like you can see, such a 4 page problem it is, right? So you should be able to read that comprehension and understand, in summarize it up in 2 lines what they are trying to say. This much task you have to do yourself. Okay, after that, guys, you will have to solve hard unseen DSA question given to you. The hard unseen DSA question given to you, you will have to solve it. So students generally do standard DSA problems, standard DSA sheets, 100, 500 lead code, easy lead code, standard GFG problems, and love bubble driver sheet. That is not enough. In online assessment, a new story based DSA question is going to come which you have not seen before. So you need to practice many new hard unseen questions of DSA of different patterns to crack the online assessment. So if you want to check out, you can check out our 850-hour DSA plus hard level DSA plus OA plus CP training. Okay, this is the best in the country, and we have way too many selections on a daily basis. Okay, you also get personalized one-to-one mentoring with me and many more things to make sure you generate the best result possible in your particular case. Okay, also, guys, congratulations to our student who has cracked off campus 50 LPSD offer from Amazon recently. So make sure you also become like that in the future if you're watching this video. Now, guys, this problem is based on graphs. That's why, guys, you should know about graphs in advance. Okay, I will just try to give you a little bit prerequisites. You need to know about graphs. Okay, so what is a graph? Graph is nothing but a bundle of nodes and edges. I have multiple videos on it on YouTube, and in my premium prerequisite course I will tell you which ones to watch. Make sure you watch them. Okay, if you're a person beginner in graphs, I will say that do a little bit of DSA coding, and then please do this prerequisite. Watch this video, then watch my premium prerequisite graph videos. Try to understand the connected component concept and maximum spanning tree concept. Only when things are done till here, na, then only come to this video and read the real question. Okay, so let's discuss about graphs now. From now this point, I will be assuming you know graph, you know the traversals, BFS, DFS, and all those things. Okay, graph is nothing but a bundle of nodes and edges. Okay, it is just a bundle of nodes and edges. So let me draw some particular graphs for you people. Okay, so let's do it quickly. So let's say n equal to phi and m equal to, let's say, phi. So n means number of nodes, so there needs to be 5 nodes. Can you see 5 nodes are there in this graph? And m equal to 5 means 5 edges should be there. This is edge number 1, this is the second edge, this is the third edge, guys, this is the fourth edge, and this is the fifth edge. So that's what I'm trying to say, is that this is a graph of n nodes. These are the nodes, right? First node n1, second node n2, third node n3, fourth node n4, and fifth node n5. Like you can number it in any way you want. Okay, like you can call this third node n3, this as n4, and this as n5. Okay, So these things are clear to you and you're really doing great at it, right? I know you are doing great because you are my student watching my video. So guys, in this graph now you should know how to do BFS and DFS. BFS and DFS are way to travel the graph. So, how to travel the graph and how to do those things are explained in this videos with the detailed codes in C++, Java, Python. Please go through them. Now I will discuss about the connected component concept of the graph. So guys, if I give you this graph, can you guys tell me how many connected components are there? In this graph, first of all, how many edges are there? One, two, three. There are three edges. So m equal to 3. M is denoted by the edges. How many nodes are there? 5 nodes are there. So 5 nodes are there, guys, lovely students, and there are 3 edges. How many connected components are there? See, this graph is fully connected. This is the first connected component, and this graph is also fully connected. So this is the second connected component. So I love you, student. The thing is that there are two connected components in this graph. So hopefully you guys understand if what is the meaning of a connected component means. If this is a connected component one na means you can travel anywhere from here to here to there to here. You are allowed to travel like that. But if two nodes are in different component, for example, node number 2 is a part of first component, and node number 4 is the part of second component. It means you cannot travel from 2 to 4. You cannot travel from 2 to 4. There is no path from 2 to 4. That's why they are in different component. So I will make graphs. You can like literally feel the components now. Okay. How many components are there? This is the component number 1. It is separate. Basically, how many parts are there? This is the second component. This is the third component. This is the fourth component, and this is the fifth component. So 5 components are there. So whenever I give you a graph, you should be able to tell me how many components are there. Till now we discussed the graphs which are undirected graph. Okay, basically if there is an edge from 1 to 2 means you can travel from 1 to 2 and also in reverse. And unweighted graphs, the weights we did not mention. For any edge I never mentioned the weight. Till now I did not ever mention the weights. For example, this is my graph. I never mentioned what is the weight of this edge. We assume that all the edges have their weight as 1. But what if I now consider a weighted graph? Then what will happen? So guys, always remember, if I give you any graph now, this is a very important concept. If there is a graph with n nodes and a single component, only one component is there in this graph, then if it has n minus 1 edges, then it is guaranteed that it is a tree without any cycle. But if it has greater than equal to n edges, then it is not a tree. Not a tree means there can be a cycle. For example, like let's say n equal to 5. Try to make any graph n equal to 5. Try to make any graph of 5 nodes with a single component. So only one component should be there. What will happen? Node 1, node 2, node 3, node 4, node 5. So the theorem says that if the edges are equal to 5 minus 1, n minus 1, 4. If there are 4 edges, then it is a tree. How many edges is there? First edge, second edge, third edge, and the fourth edge. So this is a tree. Why is this a tree? Because there is no cycle. This is a single connected component and there is no cycle in it. But guys, if there are more than four edges, then there will be a cycle. If there are more than four edges, there will be a cycle. So let's add any extra edge. Now how many edges are there? Now there are five edges. We break the rule. The rule was that there should be four edges, n minus one edges. But now I make one extra edge here. Now there is a cycle. Can you see? From 3 to 4, 4 to 4, 5, 5 to 3, you are in a cycle now. So your graph has a cycle now, baby. So you guys understand these things, right? You must be enjoying it a lot. So any single component will always have minimum n minus 1 edges. If it has n minus 1 edges, like remove this. If it has n minus 1 edges, then this is a tree. Tree has no cycles. But if it has more than n minus 1 edges, all those extra edges are creating a graph or a cycle. Okay. So like this much deep knowledge and deep focus you need to have. Okay. So let's just chill out and chill as much as possible. So these many things are clear to you people. Okay, fine. So how to find the connected component, number of connected components? You can check the code and the videos are also given above. Okay, like if I open it up for you people, you can go till the end and see what's happening. Okay, clear? Yeah, Ram Ram. You just need to be very strong and positive in your life. You need to be very strong and positive. If God is with you, nothing will happen to you. Just have faith in God. So guys, Ram Ram, this thing is done. Now what else to do? Okay. Maximum spanning tree I need to discuss. This much I need to discuss before I proceed with the GoldMan Sachs online assessment for you. Okay. So guys, now please make sure that you know all the things I said till now. Okay. Maximum spanning tree means I will give you a single component. I will give you a single component, single connected component. I will give you a single connected component. It will have n minus 1 edges, or it can have more than n minus 1 edges also it can have. Okay. You have to tell me which edges to remove. Which edges to remove to make it a tree. To make it a tree. Tree, but the tree should have maximum sum of edges. And the earlier thing I will just write it here, and that thing is, if a single connected component has n nodes and n minus 1 edges, then it is a tree. It is a tree without any cycles. But if it has strictly greater than n minus 1 edges, then it is not a tree. It has cycles. So guys, now for the maximum spanning tree, na, let's say I make this graph for you. How many nodes are there? Four nodes. You want to make it a tree. Tree will have n minus 1 edges. 4 minus 1, 3 edges for this single connected component. But there are four edges here. So any one edge you need to remove. Any one edge you need to remove. This much you understand, right? That we want three edges to make it a tree. We want a tree. We don't want a cycle, because currently there is a cycle 1, 2, 3, 4, 1, 2, 3, 4. So which edge will you remove? You need to make sure that this graph has three edges. Currently there are four. So you can randomly pick any edge and cut it up. If you cut it like this, the new graph will be 1, 2, 4 till then 3, then 2. Like this. This will be the new graph. Done, 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 done. So this is the basic thing which we have to observe here. And now here there is no cycle, like 1, 4, 3, 2, and then the end. It ends. The path ends. There is no cycle. So this much is clear, right? Now let's say this is your like there are five nodes here. There are five nodes here. Okay, there are five nodes, and the number of edges are how many? You want only four edges, right? You want four edges to make it a tree, but currently how many edges are there? One edge, second edge, third edge, fourth edge, fifth edge, sixth edge. So one, two, three, four, five, six. There are six edges. Okay. So there are six edges, but you want only four edges to make it a tree. So you need to remove two edges. You need to remove two edges. So how will you decide which two edges to remove? Let's say in this graph you can see that you should remove this edge, right? And you should remove this edge, right? Then the tree will be looking like this, which has no cycles in it. See, this is a normal tree, no cycle is there. But when the edges were there, because of the two edges, two cycles were there. See, like this, one cycle like this, and another cycle going on like this. Okay. So earlier these things were happening. So guys, you understand to make a spanning tree, you need to remove the extra edges. But now what if each edge has a weight? What will you do? This edge is weight 1, 2, 3, 4. Now you need to make it a tree. You want three edges, but currently there are four edges. So you need to remove 4 minus 3. One edge you need to remove. Which edge will you remove? Which edge will you remove? You can either remove this guy or this edge or this edge or this edge. Which one will you remove? Think about it, lovely student. Think about it. So the solution to the problem is that you will remove the smallest edge. You will remove the smallest edge. This one with the weight 1. Now the tree looks like 1 to 4, 1 to 4 of weight 4, 4 to 3 of weight 3. Now guys, whatever tree without cycle we have got now, its sum of edges is maximum 4 plus 3 plus 2. That is what we call as maximum spanning tree. So guys, did you understand? If I give you any tree, let's say I give you a tree of five nodes and six edges, like this: one, two, three, four, five, 1, 2, 3, 4, 5, and one more edge. Let's say 1 2 4. Now each edge has some weight. Okay, 1, 2, 3. You know that you want only 4 edges, but currently there are 6 edges. 6 minus 4, 2 edges you need to remove. But you want the remaining tree to be a maximum spanning tree. After you remove the 2 edges, now the remaining tree should have the maximum sum of edges. So which one you will remove? You will remove the two smallest edges. Now is it not common sense? You will remove the two smallest edges. Just telling you common sense. There is a proper greedy Kruskal algorithm to deal with this, by the way. But in general theory, I'm saying that you should remove the smallest edges, right? You will remove this edge with weight 1, and you will remove this edge with weight 2. Now this is a proper tree with no cycles, and the sum of the tree is 3 plus 4 plus 5 plus 6, which is the maximum spanning tree. So if you don't know about the spanning tree concept now, don't think that you just have to remove the two smallest edges. Sometimes that is not allowed. Sometimes you have to check the cycle, because removing the two smallest edges can lead to breaking of the graph. You cannot break the graph. You need to maintain a single component. This was a simple case. That's why it worked very simply. Okay. So this is the maximum spanning tree concept. Like you want, you can see the hard case also. like 1, then 2, then 3, like this. Okay. Let's say 4 is also there and this is also there. Okay. Now let's think about it. No. Let's make it a little bit more complicated. Let's say this is the case going on, right? This is the case going on. Now let's say from 1 to 4 you make some edge, right? Right. And then from let's say everything is all right only. Then let's say you make an edge from 3 to 5. Okay. Clear? Clear, sir. Now the things are like this. Uh, Let me think about it a little bit. Let's say this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is 7. Now you might think, sir, there are 1, 2, 3, 4, 5, 6, 7 edges are there, sir. And we only want 5 minus 1, 4 edges. So 3 smallest edges I will remove, sir. So you will remove the edge with weight 1, edge with weight 2, right? And the edge with weight 3, right? This is the normal brain will think, right? So let's remove them. And then the edge with the weight 3, right? What will happen after you do that? Now the graph will look like this: node 1 alone, node 2 alone, and node 5 sticking with node 4, and node 4 sticking with node 1, and node 4 sticking with node 3. Okay. And the edges are intact. But now can you see this graph is not a tree anymore? Tree needs to be a single connected component, and then there are three connected components. Okay. So whenever you're doing something now, you better be very very careful. Okay. Like there are not three connected components, sorry, this two is of the graph only. There are two connected components now. So you cannot directly do this, you cannot directly remove the smallest edges. You need to follow a special graph algorithm, which is Kruskal algorithm. Kruskal algorithm sort the edges by their weight. So you will have all your edges from minimum weight till the maximum weight. You will try to remove the minimum edge, or the maximum edge, depending on you want maximum trees, maximum spanning tree or minimum spanning tree, and get the job done. If it is not working, you will check is this edge a part of a cycle or not, and then you remove. So this much you can study from my prerequisite videos. Okay. So hopefully you understood that this is the concept of connected components and the maximum spanning tree. Now, Ram Ram, Ram Ram. God is very important. Ram Ram, Ram Ram. So now let's go to the real question. So guys, break and add. You are given a graph not necessarily connected of n nodes and n numbered. There is one based indexing we are using, right? The nodes are numbered from 1 to n, and there are n minus 1 edges. Always have full clarity in your life to generate the best possible results. Okay. You can break any edge disconnecting the pair of nodes in one operation, but you must add the same edge between a different pair of nodes. The cost of one such operation is the cost of the edge being disconnected and added again. You can perform the operation any number of times. Determine the minimum total cost to make the graph connected. So guys, this problem is like literally very easy for you if you know all the deep concepts of connected components and maximum spanning tree by Kumar Kesar. So guys, this graph is given to you. Okay. uh 1 2, okay, 1472. Okay, let's draw it up. 1 4, let's see, 4 1, then 2 and 7. Okay. And then there is this node is with the value 5, right? Value 5. Then there is one more node with the 368, right? 3 6 8. 3 6 8. 3 6 8. 3 6 8. 3 6 8. 3 6 8. 3 6 8. 3 6 8. 3 6 8. 3 6 8. 3 6 8. 3 6 8. 3 6 8. 3 6 8. 3 6 8. 3 6 8. 3 6 8. 3 6 8. 3 6 8. 3 6 8. 3 6 8. 3 6 8. 3 6 8. 3 6 8. 3 6 8. 3 6 8. 3 6 8. 3 6 8. 3 6 8. 3 6 8. 3 6 8. 3 6 8. 3 6 8. 3 6 8. 3 6 8. 3 6 8. 3 6 8. 3 6 8. 3 6 8. 3 6 8. 3 6 8. 3 6 8. 3 6 8. 3 6 8. 3 6 8. 3 6 8. 3 6 8. 3 6 8. 3 6 8. 3 6 8. 3 6 8. 3 6 8. 3 6 8. 3 6 8. 3 6 8. So guys, this is this. Now they are saying that make it in a single connected component. Currently, how many components are there? This is the first component, this is the second component, and this is the third component. Three components are there. So how many edges will you need to convert them to one component? Two edges will be needed. If there are y number of components or x number of components, then you will need x minus 1 edges. Why? Array, this is common sense actually. This is component number 1, right? This is the second component, right? This is the third component, right? So three components you can join by two edges. How? You can make one edge like this, na, edge number 1. And then you can make the edge between the second component and the third component. So if there is component 1 separate, component 2 separate, component 3 separate, so one edge here and one edge here will join them. So there will only be two edges required to join three components. So guys, they are saying that only, that hey bro, yes sir, please join these, convert them into single component. So you will say, sir, I will join like this and I will join like this. Yes, your solution is correct. Initially it is correct now. So that same concept I have written here, that given a graph with multiple connected components, remove some edges and add those edges again in the graph to convert it to a single connected component. Do it in minimum cost. Each edge has a weight. Okay, each edge has some weight. So guys, if there are three connected components, you will need two edges to make them in one component. Okay, so you need to remove three edges from the other part of the graph. Bypass surgery, we remove the veins from the leg part and put in the heart part. So same thing here. That was an extreme example, sorry, Ram Ram. So there are three components here: first component, second component, third component. You know that you want one edge here and the second edge here, but from where will you bring e1 comma e2? From where will you bring? From the same graph only you will bring e1 and e2. What can you do is, from the first component you can break this edge 1 to 2. You can break this edge 1 to 2, and let's say this is the edge. Let's say edge 1 to 2 is e1. Okay, so I break e1 here and I use this edge to connect 1 to 5. And similarly, let's say 3 to 6 is okay, it used to look like this, na, 3 6 8. Yeah, one more was there. This is E2. Let's say the edge from 3 to 8, let's call it as E2. So you break the edge from 3 to 8 and you connect 3 to 5. Now what will happen? This will be a fully connected component. So guys, before the start of the question only, you just need to know how many edges are required. There are three connected components, C1, C2, C3. So you need two edges. You need two edges. So you will break two edges. You will break two edges and you will add those two edges again in a different fashion. So you can break this one, you can break this one, and this edge you put it like this, and this edge you put it like this. So the 1 to 2 edge which you broke, you join it as 1 to 5, and the 3 to 8 edge which you broke, you join it as 3 to 5. But guys, now the question is, sir, which edge should I break? Breaking edge has a cost. Breaking edge has a cost, guys. Big, the cost is nothing but the cost of that edge. So let me give you the example here. 2371. 2371. Then the next one, which is again very, very important. The next one is again very, very important. It is 475. 475. So observe this graph deeply. Observe this deeply, guys. Observe this deeply. Now you only think, you need two edges. You need two edges. Which two edges will you take? God has given you brain, right? This is a single connected component. This needs to be a tree. So how many extra edges it has, guys? ये एक सिंगल कंपोनेंट है. इसको ऐसे का ऐसा रहने के लिए कितने एज चाहिए? सर इसमें देर आर फोर नोड्स हियर. There are four nodes here. It only needs three edges. So one extra edge is there here. One extra edge you can remove without affecting this component. It will still remain a single connected component. And here also you can see that there are three nodes. So it needs only two edges. But there are three edges here. So 3 minus 2, one extra edge is there. So guys, which one extra edge will you break from this component and that component to get the job done? You will break the edge with the minimum cost. See, this edge has value as 1. So you break this one. You will break the edge 4 to 1, which has a cost of 1. So break it up. Even after you break it up, this graph is still a single connected component. Here, you will break the edge 3 to 6. 3 to 6 with the cost 4 because it is the minimum cost. So break it up. Still it is a single connected component. 3 to 8, 8 to 6. Now this edge of size 1 I will of value 1 I will connect it here of value 1, and this edge of value 4 I will connect here. Now this full thing has become a single connected component. Full thing has become a single connected graph now. And what is the cost? 1 plus 4. So guys, what is the solution? The solution is pretty simple if you understood what I was trying to say. You will have to travel each connected component in this graph. What will you do, guys? You will travel each connected component and you will try to find out how many extra edges are there. I will travel this component, the first component, then I will travel second component using my BFS, DFS, and then the third component. I will try to find the extra edges which are not required. Which are the extra edges here? The extra edge which is not required. What is the meaning of the extra edge? I taught you this concept just few minutes before. If you want the graph to remain as a tree, see the total number of edges are n minus 1, so this will be a tree only. If you want it to be a tree with a single connected component, you can remove all the extra edges after n minus 1. So there are 4 edges now, so one extra edge is there. But guys, which one will you declare as extra? That one which has the maximum cost. And here's, sorry, that one which has the minimum cost. So 1. So you know that there is an edge of size 1 which is extra here. Here which is extra? This 4. Sir, this is extra. So like this you will create an array of all the extra edges. You will create an array of all the extra edges. Then you know how many edges you need. Let's say in this case you need 2 edges. So from these extra edges you will take the 2 minimum edges. So the cost will be minimum to convert it in a single component. Like let's say I will give you one more example now. Let's say 1 to 2. Okay. Let's take the example like this. This edge is of weight 1, 2, 3, 4, 5, 6. Okay. And let's say it is like this. Now there are two components. You have to convert them in one component. What will you do? Think about it. Either remove or add. So this is component number 1. This is component number 2. So you need one edge. One edge is required to join them. One edge is required. Now let's try to find the extra edges in each one of them. So which are the extra edges here? Sir, there are 4 nodes. So 3 edges are needed. But we have, let me check how many edges we have. We have 6 edges. So 3 edges are extra. How many extra are there? 3 extra edges are there. Which are those three edges, extra edges? The smallest three ones. You will run the maximum spanning tree algorithm on this component, and the maximum spanning tree algorithm will tell you which edges you don't need, such that the remaining tree will have maximum sum of edges. So automatically that algorithm will remove the smallest edges which are not needed. So here you can remove one, you can remove two, and you can remove three. Even after that, the tree will be of 4, 5, 6. Maximum spanning tree will remain. So extra edges are 1, 2, 3. So guys, I'm making this extra array. Okay, extra array means the edges which are not needed, you can remove them anytime without affecting the whole graph. Edge with value 1 is not needed, 2 is not needed, 3 is not needed. So how did you come to know? You will run a maximum spanning tree algorithm on this component. In this graph, guys, there are 4 nodes. 3 edges are needed. 1 edge is extra. Which is extra? The edge with the minimum weight, right? So run the maximum spanning tree algorithm. So maximum spanning tree algorithm will include 2, 4, 3, and it will discard this one. So 1, 2, 3, 1. So guys, these are all the extra edges. You can remove them if you want to. We have not still removed them. You can remove them if you want to. Even if you remove all of them, there will still be two connected components. That is the meaning of extra edges. But guys, now you need only one edge to convert it into single component. You only need to connect 2 to 5, right? One edge is needed. So from the extra edge, which one will you use? You will use the smallest one from the extra edge. So if you need one edge, you will take the smallest from the extra. If you needed two edge, you will take the two smallest. So you will sort the extra array basically. And the problem is solved, guys. So hopefully you guys enjoyed it. Okay, nice, brilliant problem, right? So if there are three connected components, you will need two edges to make them in one component. So you need three edges from the other part of the graph. So how to know which extra edges can be removed without affecting the current number of connected components? Find the maximum spanning tree of each component. This will let you know all the unrequired edges in the graph with minimum weight. Let us say you come to know that about 4 edges are there which with minimum weight which are not required. So you can remove them without affecting the current number of connected components. But you also know that you only need two edges to make the whole graph one component. So from the 4 extra, see here there were how many extra? Yes, our brilliant program where students keep cracking Google and keep becoming expert on code forces. सो इन दिस केस हमको एक ही एज चाहिए था, बट हमारे पास चार चार एक्स्ट्रा एज है, तो चार एक्स्ट्रा में से सबसे छोटा वाला यूज करोगे ना, तो वैसे ही इस केस में मैं बोल रहा हूँ कि अपने पास चार एक्स्ट्रा पड़े हुए, बट हमको दो ही चाहिए, तो दो सबसे छोटे वाले एक्स्ट्रा वाले में से उठा लेंगे. If you needed two edges from here, you would take the two smallest. You want one, you will take the one smallest, so that the cost is minimized. You only need the two smallest edges of the four extra edges found. Take them, use them to make the one component, sum of two smallest edges out of all the unrequired edges. So if I go towards the coding part, guys, you can see this nice thing going on. The Kruskal algorithm you are running, first of all, you're taking in the graph. You are watching this, I assume you have done all the prerequisites of graph. You're just trying to find how many components are there in the graph. The number of edges needed to make it one component is total component minus one. Okay, three component then two edges, right? N minus, like total number of components minus one. If n is the number of connected components. Anyways, here we are using component dot size and this. So these many edges we require. Now we will try to find the unnecessary edges. Okay. So once we have unnecessary edges, we now need needed edges from them, right? So we will sort the extra array. This is the extra array, extra edge array. From the extra edge array, I will only travel till the needed edges. Let's say only two are needed. So only the two smallest I add in my main cost, and done, done. So hopefully you just liked it. Okay. So with the name of God, Ram Ram, everything should always start and end in your life with the name of God, Ram Ram. So guys, see, always stay strong, never get demotivated. God is always with you, okay? God is always with you. So always stay strong. Have full faith in God. You need to have as much faith as possible in God. So Ram Ram.